Next, we'll talk about how LiDAR can benefit the transportation industry. One big thing that influences transportation decisions is traveler behavior. For example, how cars and pedestrians are using an intersection, like drivers who insist on stopping beyond the stop bar, or how cars and pedestrians behave under certain conditions, like pedestrians who get impatient and decide to cross instead of waiting for the walk indication. These behaviors force transportation engineers to take ideal designs and modify them to compensate. For example, the drivers who pulled past stop bars and has forced the installation of loops to be extended past the stop bar so these drivers still get picked up. To make the problem even more complicated, the behavior of travelers differs between intersection to intersection, highway to highway, and roadway to roadway. Upstream conditions can also influence traveler behavior. For example, drivers stuck at a red light too long may speed to make sure they don't get stuck at the next light, causing maybe a dilemma scenario, or running a red light trying to beat that yellow light. So understanding how to make improvements involves understanding traveler behavior. But how do professionals figure these details out? In a few ways, but the tools used have their own limitations. Here are some examples. Starting with the most basic, drivers calling to make complaints. When you get one of these, the problem's likely been going on for a while. Although addressing the problem at some point is better than never, you're still addressing it much later than it should have taken. You're always going to be lagging behind on addressing the problems, which is not where you want to be. So in comes analytic systems like SPM, signal performance measures. These let you identify inefficiencies and problems before the complaints come in. They've been incredibly beneficial to the industry in helping make decisions. The problem is they're built on top of systems that only provide very limited details. For example, turning movement counts. Because current sensors don't know which way cars are actually turning, they have to base it on the primary movement at a stop bar zone and assume the car went in a specific direction. So lanes that permit something like a through or a left and a right, they typically get counted as a through movement. So it's not really about which way the cars are actually turning, but an assumption based on what information is available. It also leads to a bit of guessing. For example, let's say you see a high amount of split failures at an intersection. The next question that pops up is why? The issue is these systems don't have access to enough information to provide an accurate answer to that question. Instead, professionals have to look at other metrics in order to infer what might be going on, essentially an educated guess. Some SPM systems will do this for you, but it doesn't change the result. It's still an educated guess built on limited information. So how do you get more detailed information? Have a technician sit at an intersection to observe it. This will definitely give you the level of detail that's needed to make good decisions to solve problems. Even with the investment, the technician may not catch everything because humans are fallible. When you start considering the option at scale, it's not practical at all because technicians can't possibly observe every intersection under their responsibility. Now, if we reflect on those tools, it really sounds like if we could merge the level of detail from technician observations with SPM systems, transportation professionals would have an incredibly powerful tool to answer those sophisticated questions like, why are we getting split failures? That's where LiDAR comes in. It has access to information just like technicians observing an intersection. We can now build tools on top of that to begin answering questions like, why are we getting a lot of split failures? Or what turns are drivers actually making? This lets us build systems that can answer sophisticated questions so that transportation professionals can make decisions to boost efficiency and safety on our roadways. So what detail is LiDAR providing in order to achieve this? Access to individual traveler behavior. LiDAR provides access to behavioral information because it tracks travelers individually within the perception region. With LiDAR, each traveler is assigned a unique ID. This ID persists as they move through the perception region. This ID even persists when transitioning between multiple sensors as long as they're part of the same perception region and fusion. This allows us to track and observe how each traveler uses an intersection, roadway, or highway, just like technicians observing an intersection. This means we can track individual traveler behavior. So what benefit is that though? It allows for real-time intervention. For example, extending red clearance times for belated walkers, adjusting crosswalk timing based on pedestrian demand, extending red clearance times for dilemma zone scenarios, advanced warnings for jaywalkers. It also benefits analytics because it allows you to answer sophisticated questions like, why are we getting split failures? Are queues maxing out? Why are people running the red light? How does lane balance look? Are cars getting too close to pedestrians? How long does it take for each pedestrian to cross the crosswalk? Just to name a few. Individual behavior tracking also improves existing analytics. For example, SPM turning movement counts. LiDAR knows which way cars are going, so we know the actual turn each car makes instead of assuming, which includes some harder to derive ones like U-turns and right turns. SPM split failure detection. Instead of plugging data into a split failure formula from a system based on limited information, we can now observe individual cars to see if they made it through the light or not. These are just some of the improvements that can be made. Lastly, let's talk about CCTV systems capable of individual tracking. These systems are limited to camera viewport. So to compensate, multiple cameras are usually installed. The problem, though, is that you can't persistently track travelers as they move between camera views. LiDAR can accomplish this because you fuse the LiDAR data together into one big sensor and view. So essentially, travelers don't leave the view, thus giving us that persistent tracking. The benefit that LiDAR brings to transportation is privacy, which is an important topic these days. And it's a large concern to the public, especially with the rise of more sophisticated technology as time goes on. However, transportation agencies need more sophisticated information on travelers. This is so that they can make informed decisions to improve efficiency and safety on the roadways. Since traveler behavior is what influences most transportation decisions, the more behavior details they have access to, the better decisions they can make to achieve that safer and more efficient roadway. Some say that CCTV systems are the answer to this, but the public doesn't trust CCTV systems, even though agencies don't generally collect personally identifiable information through these. The public still sees it as a threat based on the fact that they could collect that kind of information. So how do we balance privacy while still providing that rich traveler behavior transportation agencies need? By using LiDAR, because it preserves privacy. You can't see faces, you can't read text, and you can't run the data through recognition software to link them to specific people. But it still delivers that high resolution details that agencies need about traveler behavior. With LiDAR, the public can be confident their privacy is being protected. For example, even though LiDAR can track individual travelers and how they move through a perception region, it cannot make out license plates or facial features at a level of detail that could be linked to them. The persistent tracking also doesn't persist outside of perception regions. For example, a vehicle who travels through one intersection then starts traveling through another. Both operate independently and have separate perception regions, so they won't be able to associate the traveler as the same one moving between them. This quells public concerns of being able to identify them. The next benefit of LiDAR for the transportation industry is that it can easily adapt to just about any geometry and occlusion problem. Every road and intersection is different. Some sites have blind spots, some suffer from occlusion issues either due to infrastructure being in the way or large vehicles blocking views. Some have large areas of interest or detection needs. LiDAR adapt to these problems. For large areas, you can simply add more LiDARs to get the coverage you need. For strange geometries, you can strategically place LiDARs to reach those odd turns, hills, and blind spots. To tackle occlusion, you can simply add another LiDAR so that if one of them is obstructed, the other can still detect those travelers. No matter how many LiDARs you deploy, the perception software will merge all the LiDARs together to act as if it was one giant sensor. This ensures you can get the detection performance you need no matter what the site is. Another benefit of LiDAR in transportation is that detection zones are much more sophisticated, versatile, and malleable. They're still an important concept when using LiDAR, but don't think of them like loops or video detection. For example, in most video detection, loops in most video detection only report a binary state, occupied or not occupied. They don't know if 1, 2, or 3 cars are on top of them. Only that something is on top of them. They don't know how fast each car is going, unless you combine multiple loops and throw in a processor to compute it. They don't know how long each car has been on top of them. They have trouble detecting some types of travelers like motorcycles and bicycles. The image on the slide shows an example of a set of detection boxes that the perception software has configured in it. Unlike loops and video detection, you can precisely carve out the zones in any shape you want. Although this example, they're only rectangles, the perception software is not limited to that shape. While configuring the zones, you can observe travelers cross them and make fine-tuned adjustments to really dial in the behavior you're looking for, as you see in the clip on the right. You get a lot of control when setting up your zones using LiDAR. So how are LiDAR zones significantly more sophisticated than video and loop detectors? They can track individual object movement through each zone. They know when each object enters and exits them. They know how long each object occupies them. They know the path objects take as they move through them. They know how many objects are occupying them. They know when objects are occupying more than one zone at a time. This means we know exactly what each traveler is doing as they move through these zones. One really large benefit to a system like this is we can make adjustments to the zones at almost no cost or disruption to the service. We can add more zones if we determine there's a need for them in the future, remove zones if we no longer need them, fine-tune existing zones when we determine changes are needed. We can make temporary adjustments when needed in situations like construction impacts, all while the system is live. Zone usage is not limited to just one use case either. If you strategize your placement and design of zones, algorithms can use these same zones for different purposes. We'll have some demonstrations of that later on in the presentation. The next benefit is that they're resilient to change and obsolescence. You've got one of these systems installed, but how does it handle changes and needs over time? Change is inevitable, so the system needs to be flexible enough to allow for change. LiDAR is positioned to support that. For example, construction projects that force you to shift lanes around. Loops can't be moved, and cameras may need to be repositioned, which could reveal new problems that can't be solved. Then you start throwing things into recall to compensate for that. With LiDAR, simply modify the zone configurations in the software and you're good to go. Temporary road studies. Sometimes this involves placing something like pneumatic count stations and maintaining those for the study durations. With LiDAR, you can simply add a zone into the virtual scene and no maintenance required or physical device deployed. When the study is done, they can be deleted. Lanes are added, removed, or modified on highways and intersections. This is usually quite expensive because it may involve installing new loops or replacing cameras. With LiDAR, all you need to do is adjust the existing zones, remove zones that no longer exist, and add any new zones within virtual space. The cost for this is a small amount of time. Future changes, needs for new use cases, or novel DOT initiatives. Most of the time, you need to install new hardware to support these, which is going to be costly. With LiDAR, it's really only a matter of developing the algorithms to process the LiDAR data for those new purposes, which is something the integrator AI helps with, as you'll see later in the presentation. This means the LiDAR system can continuously be repurposed over its lifetime. Next, we'll examine cost and value. Cost has a huge impact on deciding what systems to purchase. That's no different with LiDAR. The price point of LiDAR has been a concern for agencies for a while because it used to be quite expensive to purchase. The cost of these systems has gone down and getting closer to the cost of current detection systems. However, one thing that is often not considered is the value LiDAR systems can bring when you do choose them. You're not just buying a basic detection system specialized in one thing anymore. The level of detail LiDAR provides opens up for many more use cases that can be accomplished. For example, deployed on a highway segment, you have your typical analytics, speed, volume, occupancy, but now you also get wrong way driver detection. You can detect travelers blocking the right of way. You can detect pedestrians and cyclists that shouldn't be on the highway. You have access to information rich enough to pass on connected vehicle systems and a system that can be extended to almost any new use case that comes up in the future. Deployed in an intersection, you have your typical actuation-based needs, but you now also get actuation filtering based on classification. You can now detect red light runners, get more accurate statistics. You can add dilemma zone support. You can set up dynamic pedestrian crosswalk timing. You can detect wrong way driving. You have access to information rich enough to pass on connected vehicle systems and a system that can be extended to almost any new use case that comes up in the future. These systems can easily be extended to support just about any new use case that may come out, since the information they provide can be adaptable to them. This means you don't have to buy additional detection systems specialized in those specific use cases. Just use what's already deployed. It may require a cost to develop an algorithm to handle the use case, but this is minor in comparison to buying an entire system to install for one purpose. The value that you get easily surpasses the initial cost. And with that cost getting closer to existing systems, it makes the decision much easier to make. Here's some use cases that you can take advantage of when using LiDAR deployments. Keep in mind, these are definitely not all of them new use cases that LiDAR enables us to achieve. These are separated into two columns, safety and efficiency. Although some of these use cases may actually qualify for both, but they're placed in the column that we felt most accurately categorized them. As I mentioned in the previous slides, a really big advantage with the LiDAR solution is that it's fairly easy to extend when trying to support many different use cases at once. I'll actually demonstrate this when we get to the integrator AI portion of this presentation and show some of our deployments that accomplish this. As new use cases come out, it's really only a matter of developing the algorithms to process the LiDAR data for those purposes, so you can continue to use the same system long into the future. I'm not going to go over all of these, but there are a few use cases I'd like to highlight. Wrong way driver detection. Current complaints of these systems is that they're giving false positives all the time. We believe we found a way in utilizing LiDAR and the integrator AI to essentially eliminate those altogether. And in fact, we're capable of extending wrong way detection to more than just on-ramps. For example, highways, intersections, arterial roadways, anywhere really. Ramp metering systems. LiDAR can replace loops and deal with any blind spots, occlusions, and large storage areas. It can pick up queue areas all the way out into the main street, feeding it. It can even compensate for unexpected driver behavior, for example, not pulling all the way up to the demand detection zone when it's their turn. Railway safety applications. LiDAR can detect cars when cars get stuck in a track. So why don't we notify railway authorities when this happens to help prevent devastating collisions? LiDAR can also detect people or other travelers on the track and provide advanced warnings to trains. Connected vehicle applications. With the rich details that LiDAR provides, why can't we hand that off to the connected vehicle system? Think of this as enabling connected vehicle basic safety messages for all vehicles, which is an equitable solution for those who can't afford to purchase vehicles with this technology on board. Detailed recordings and playback of events, like accidents or congestions. Think about it. An accident occurs in an intersection or a roadway and you'd like to see what happened. How beneficial would it be if you could just load up a 3D scene, play the event over on repeat, and move around the scene and observe the incident before and as it happened? How valuable would that level of detail be when trying to determine what happened and how to prevent it in the future? LiDAR certainly enables this kind of feature. Next, we'll talk about how LiDAR can benefit traffic signals and intersections. This section will be much shorter than the previous because many of the previous concepts and points apply here. But to start, we'll highlight some benefits that specifically apply to intersections and traffic signals. Then we'll offer a starting point for a versatile LiDAR zone configuration at an intersection, something we've been fine-tuning and found to be pretty effective so far. Lastly, we'll cover some use cases that can be applied to traffic signals and intersections. Starting with some highlighted benefits, targeted classification based actuations. With the rich data we get from LiDAR, we can now configure actuations to target specific traveler classes. For example, cars, bicycles, trucks, motorcycles, pedestrians. In fact, on how detailed the perception software can get, you can really fine tune what is actuating your signal now. For the main lanes, you can now configure them to pick up cars and bicycles if you want. Bicycle only lane, you can configure it so nothing else will actuate it but bicycles. Some lanes you want to pick up cars and bicycles, others you only want cars. That's perfectly achievable with LiDAR. You decide what actuations the signals on a lane by lane basis. Next is passive priority classification by classification. It can be possible to put in priority requests when certain object classifications are detected. This eliminates the need for vehicles to have onboard devices like priority preemption transmitters, which would reduce costs to the city. What about dynamically changing signal timing to make intersections safer and more efficient? For example, 20 pedestrians show up waiting for their turn to cross. This is more than normal, and static timing may not be enough for them. This would be a good scenario to increase the walk time they have before the walk indication comes up to ensure everyone has enough time to make it across. This improves safety. What about if there are only 3 pedestrians waiting to cross? Now we can adjust time to be much more shorter, which improves intersection efficiency. What about when pedestrians don't make it across in time before opposing traffic is permitted to go? In those scenarios, we can dynamically add time to red clearance. This will give the pedestrian more time to clear the sidewalk before opposing traffic is given the green. This improves intersection safety. What about dilemma situations? We can increase red clearance times when dilemmas are detected to ensure opposing movements are not given a go until the intersection is safely cleared, which improves intersection safety. There are many more things we could do to dynamically change timing behavior to both improve safety and efficiency at the intersection. With the availability of rich data, we can also add new metrics to analytics that were not possible before. Since we have access to traveler behavior throughout their time utilizing the intersection, we can add better insights for engineers to analyze both performance and safety of the intersection. Knowing how VRUs and vehicles are using the intersection is critical for transportation professionals to make good decisions and improve safety and efficiency. LiDAR provides that detail to professionals.